Oh, hey, can't see you there. Welcome to Invertigo. Aren't you tired of playing these boring video games?
I'm bored.
Did you just say that you're bored? Haven't you looked to your left?
What? Invertigo! Invertigo!
Let's talk to a pro to see what goes on behind the perfect throw in Invertigo.
So, Mr. Miller, how long have you been playing Invertigo?
Well, it wasn't until I was practicing in my basement until, as my sponsor Nike would say, just do it. When I realized, I should really take this full stride and really take this competitive.
So tell me, how do you pull off the perfect throw?
It's all about force. Remember that force is a vector. I aim to apply a force that will be parallel to the surface and in the same direction of motion. Just do it.
So how hard do you need to throw it to get it through the loop?
It's funny you should ask. If you want to know the answer, just ask my agent. Just do it.
To understand how hard a marble must be thrown in order to make it through the loop in Invertigo, we must first look at the physics of the marble as it is traveling through the Invertigo track. It all starts with an applied force. Here, Andrew applies a force on the marble that will cause it to accelerate. This acceleration causes the ball to have an initial velocity as it leaves Andrew's hand and enters the cone. Remember that force, acceleration, and velocity are all vector quantities and therefore have direction, though, for the purposes of this game, we are only interested in the component of those vectors that are in the same direction as the direction of motion of the marble. Here, the marble has left the cone and is about to enter the loop. At this point, we set the height of the marble to be equal to 0. Therefore, it only has kinetic energy due to its velocity and 0 potential energy. Now remember, the marble will always lose energy due to work done by dissipative forces, though, for the purposes of this explanation, we will regard the Invertigo track to be frictionless. Here the marble has entered the loop and reached its highest point. Not only does it have a height, which gives it potential energy, but it has a velocity, which gives it a kinetic energy. Because energy is conserved, we know that the sum of the potential energy plus the kinetic energy of the marble at the top of the loop would have to be equal to its kinetic energy at the bottom of the loop as it is entering. Therefore, we can conclude that the force that you initially give the marble would have to give it a kinetic energy greater than its potential energy at the top of the loop. By the way, I'm Andrew's agent.
Thank you very much for your time, Mr. Miller. It's a wrap.